Hello class. So I'm going to be going over the rocket derivation equation, or the derivation of the rocket equation. So I drew my rocket right up here, which shows the velocity of the rocket at going Vr, or V sub r, and the mass of the rocket m, which will be changing throughout the rocket's flight because of the exhaust pushing the rocket upward or forward. And I defined u as a constant velocity of that exhaust leaving the rocket, and dm, which is that small amount of mass leaving the rocket at any time. So dm is that change of mass of the whole rocket. And I also drew a free body diagram of just the rocket. So we have gravity pulling it back down at mass times g, and the external force of the exhaust pushing the rocket upward. And we can say that that force is equal to the change of the velocity of the rocket with respect to time times the mass of the rocket. So you can see that the dv over dt is the same as acceleration, so all we have here is F equals ma. Next I wrote, so we're using the concept of conservation of momentum. So I have my change in momentum equals 0 at a given time. So for this conservation of momentum to work, we're looking at this whole system, including the exhaust that's leaving and spewing out. So we have the change in momentum is equal to the mass times the change of velocity of the rocket. So I have m dv sub r plus the velocity of the exhaust times the mass of the exhaust leaving the rocket. So that infinitesimal amount of mass times u. So all I did was just added up all the momentum in this entire system, the rocket and the exhaust. So solving, I subtracted u dm to one side to get mass times dvr equals negative u times dm. And solving for the dvr, we get dvr equals negative u dm over m. And remember that m is changing throughout the rocket's flight because it's continuously losing mass. Now let's only look at the rocket. So referring to our free body diagram, we have two forces acting on the rocket alone. We have that external force, which we defined as the dvr over dt times m, and we have the gravitational force pulling it back down. So for this problem, we're going to say that g is a constant negative 9.8 meters per second squared. So I wrote down my sum of the forces, going back to Newton's second law. So my sum of the forces is equal to the mass times the acceleration of the rocket, which should equal these two forces added together. So I have my external force plus mg. And then I just substituted in my external force that we defined up here. So we have MA equals dVr over dt times M plus mg. Notice we have an m in each of the terms. So we can just divide out the mass to cancel out all the masses. Just like that. Then we can also change acceleration into a differential representation. So we get dv over dt equals dvr over dt plus g. So we're doing just about the same thing as we did for resistive forces, where we used Newton's second law to get a differential equation. So now I can multiply everything by the dt to get dv equals dvr plus g dt. And then we can sub in what we found for dvr from conservation of momentum from up here. So we have that negative u dm over m. So we can sub that in for this quantity to get dv equals negative u over m dm. Then we still have plus g dt. Now we have our differential equation set up, so we can integrate through the whole entire thing. So using integration, we have the integral going from initial velocity, or v naught, to some final v. And we have integrating the negative u over m dm, so we integrate from initial mass to some final mass. And for integrating time, usually you could say t naught or initial time, but usually we say the t naught is 0. So I have it going from 0 to time t. So here all I did was rewrote the integral. So we have the integral of dv from v naught to v equals the integral of negative u over m dm from m naught to m plus the integral of g dt from 0 to t. And remember that we said u, or the exhaust velocity, is constant, and we also said g is constant acceleration due to gravity. So integrating through, this integral of dv is just v, and my boundaries are from v naught to v, which equals, and since u was a constant, I can pull out the negative u and just integrate the dm over m. And if you remember the relation, it comes out to natural log of m going from m naught to m, then plus the integral of just dt is t, and we can pull g out because it's a constant. So evaluating, we get v, plugging in v, minus the v naught down here, equals the negative u times the natural log of m minus the natural log of m naught plus g of t, and I could put minus g times 0, but g times 0 is just 0, so that goes away in our next step. In the next step, I still have v minus v naught equals u, and here I just distributed the negative into the natural logs to get u times natural log of m naught minus the natural log of m. So you see that I could just switch them and still keep the minus in there. So the negative went to the natural log of m to make minus natural log of m, and then plus natural log of m naught. So I have my positive natural log of m naught minus natural log of m. And I still have my plus gt. And then we have the relation of the difference of logs can be put into a single log and just dividing them. So we have natural log of m naught divided by m, which you see here. So we have v minus v naught equals u natural log of m naught over m plus gt. And solving for final velocity, we get velocity as a function of time. Oh, and I should put function of time and mass. So it would look something like m comma t, since it's both the function of that mass and time. So we have equals the v naught that we added over plus u natural log of m naught over m plus gt. This is our rocket equation. So if the rocket is in outer space, far enough away from Earth so that gravity doesn't have a very large effect on it, we can get rid of this term, because that g, that negative 9.8 meters per second squared, would go to 0 if it's very far away from Earth. Now, some other values to know. So thrust is defined by that external force that we defined earlier in our free body diagram, which is equal to the change in velocity of the rocket per unit time, or dvr dt, times the mass of the rocket. So we see again that it's just acceleration times mass. And then we could also sub in our relation that we found from the conservation of momentum to get that equal to negative u, or the exhaust velocity, times dm over dt. Usually this right here would be defined as the thrust. We also have what's called the burn rate, so the amount of mass that's leaving the rocket per unit of time. So we have just dm over dt, so the amount of mass leaving the rocket per unit time. And that is how we get our rocket equation. Thanks, guys.